Dear student, I am Dr. Harel Thomas, Professor in Applied Geology, Dr. Harisingh Gour, Vishwavidyalaya, Sagar. Today, I will deliver my lecture on ACF diagram. This topic I will cover under the following heads: Introduction, Phase Rule, Simplifying Components, Metamorphic Phase diagrams, ACF diagrams, and Method of Calculation. Hope it will be useful for you. Try to be regular in course. Like igneous rocks, metamorphic rocks are also composed of 9 or more than major elements like SiO2, Al2O3, Fe2O3, FeO, MgO, MnO, CaO, Na2O, K2O, and S2O. Thus, initially, it would appear that we are dealing with a 9 or 10 component system. However, the number of components in any given system is the minimum number required to define all composition of all phases in the system. Thus, since constituents like Na2O and K2O are not usually found as separate mineral phases, we can combine these with other constituents like Al2O3 and SiO2 in the feldspar, like albite and orthoclase, and thus reduce the number of components required to define our system Na2O plus K2O as alkalis. This is important if we graphically display chemically rock and mineral data in a way that is easily visualized. In fact, the best way to visualize such data is to attempt to reduce the number of components to 3 so that we can plot the composition of rocks and minerals on a triangular composition diagram. Before discussing how this is done, we first review some of the principles of 3 components compositional diagrams. The phase rule gives 1928 phases, distinct materials or state plus degree of freedom independent variables equal to components plus 2 temperature and pressure, P_S2O, PCO2, pH, oxygen phygosity, and EH. Simplifying degree of freedom, generally we ignore pH, EH, oxygen phygosity for most rock. Important for sulfide system, usually care about pressure and temperature. Assume P water equal to P total for silicates, PCO2 equal to 0. Assume PCO2 equal to P total for carbonates, PS2O equal to 0. Assuming PS2 equal to 0 and PCO2 equal to 0 in some cases, then P plus F equal to C plus 2. If F equal to 2, then P equal to C. Number of phases equal to number of components. Components equal to SiO2, Al2O3, Fe2O3, FeO, CaO, MgO, Na2O, K2O, TiO2, Cr2O3, MnO, barium oxide, strontium oxide, P2O5, S2O, CO2, F and chlorine. Simplifying components, we can plot a maximum of 3 components using triangle diagrams. Ignore SiO2 axis, S2O axis or 0, CO2 axis or 0. Assume P2O5 goes into apatite, Na2O into albite, TiO2 into rutile or ilmenite, Cr2O3 into chromite, fluorine into fluorite or apatite, chlorine into halite. Include MnO with FeO, barium oxide and strontium with calcium oxide, Fe2O3 with Al2O3 or FeO, Cl, F with OH. Subtract major elements as necessary. Components reduce to Al2O3, FeO, CO, MgO, K2O. ACF graphs Al2O3, CaO, FeO plus MgO. AKF graph Al2O3, FeO plus MgO and K2O. AFM diagrams Al2O3, FeO, MgO, K2O in tetrahedron. SiO2, CO, MgO used for carbonate system. Plot major amounts, not weights. Tie lines denotes 2 coexisting phases. Triangular subfields denotes 3 coexisting phases. Phase diagrams give the idea about the mineral combination under given pressure temperature condition. Evolution tracked by changes in diagrams. Normally F equal to 2, C equal to 3, P equal to 3. On a reaction curve, F equal to 1, P equal to 4. How to get 4 phases together? New phase appear in middle of field, new phase appear on the tie line breaks and new minerals forms if changes in metamorphism. New minerals appear and old minerals disappear. Ascola in 1915 proposed the ACF diagram as a way to illustrate metamorphic mineral assemblages on a simplified 3-component triangular diagram. He concentrated only on the minerals that appeared or disappeared during metamorphism and also gives idea about the grade of metamorphism. The chemical composition of rocks and silicate mineral is conventionally stated in terms of 10 main oxide, namely SiO2, Al2O3, Fe2O3, FeO, MgO, CaO, Na2O, K2O, MnO and S2O. It is impossible to represent graphically all possible variation in the mineralogy in a broad system of more than 3 or 4 components. Therefore, it is necessary to reduce the number of components for graphic representation. In common metamorphic rocks, SiO2 is present in excess. Quartz is constituent of many metamorphic rocks, and thus only those minerals with highest possible SiO2 content can be formed. Consequently, the amount of SiO2 has no influence on the mineral assemblages and thus need not to be represented graphically. S2O may be considered as mobile component and thus may not be considered. Similarly, Na2O and K2O may also be neglected because rocks containing alkali may have albite and potash feldspar as additional phases beside those shown in the diagram. As biotite and muscovite also contain K2O, therefore, a separate AKF used to represent the mineral assemblages and containing these micas. Thus, it is possible to reduce the component as follows. 1. Al2O3 plus Fe2O3 because Fe plus 3 substitute Al plus 3. Second, FeO plus MgO plus MnO minus TiO2 if ilmenite is present. These can be combined together because MgO and MnO commonly substitutes FeO in silicate minerals. Third, CaO minus 3.3 into P2O5 minus TiO2 if spin is present. On the basis of these considerations, Ascola neglected the minor components TiO2, P2O5 because they form accessory minerals, also neglected H2O and CO2 in view of their being mobile components. Na2O, which proxy other components, Ca in plagioclase, was also left out of consideration. Ascola reduced the remaining 7 components, namely Al2O3, Fe2O3, FeO, MgO, MnO, CaO and K2O into 3 components for this familiar known ACF diagram. Ascola in 1915 adopted the following reasons: since the divalent cations Fe, Mg, Mn have similar ionic radii, they can be grouped, that is FeO plus MgO plus MnO, as one component called F component. Assuming the substitution between the trivalent cation Al and Fe plus 3, Ascola combined Al2O3 plus Fe2O3 as component and designated it as A component. Ascola gave equal importance to the CaO and K2O, which served as the third component in his ACF diagram and K2O in his AKF diagram. The above 3 components are used by Ascola to represent the mineral assemblages of metamorphic rocks of the different phases. Method of calculation: first, weight percentage of Al2O3, FeO, MgO, MnO, Fe2O3, CaO, K2O and Na2O are converted into molecular proportion by dividing weight percent oxide by the molecular weight of the oxide. Second, in albite, the molecular ratio Na2O ratio Al2O3 is 1:1. Similarly, in potash feldspar, the molecular ratio K2O ratio Al2O3 is also 1:1. Therefore, the molecular proportion of Na2O and K2O are added, Na2O plus K2O, and an equal amount equal to their sum is subtracted from the molecular proportion of Al2O3 plus Fe2O3, that is Al2O3 plus Fe2O3 minus Na2O plus K2O. Third, A plus C plus F can now be written as follows: A equal to Al2O3 plus Fe2O3 minus Na2O plus K2O. C equal to CaO minus 3.3 P2O5 minus TiO2 if spin present. F equal to FeO plus MgO plus MnO minus TiO2 if ilmenite is present. For the purpose of graphic representation, these values are recalculated so that A plus C plus F equal to 100, that is, they are expressed as molecular percentage. On the ACF diagram, the observed mineral phases in the different rocks, with exception of quartz, albite and orthoclase, are plotted using their chemical formulae. The chemical formula is based on molecular proportion. It is possible to divide the 3 components diagram into triangular field such that only rocks whose chemical composition falls within a given triangle will be found to consist of the 3 mineral phases located at the apex of that triangle. If the chemical components of a rock lie along the joint of two minerals, only two phases are expected to be present in the rock. Thus, in the three-component system, number of phases commonly do not exceed 3. This is the main application of the mineralogical phase rule. By creating these three pseudo components, our scholar reduced the number of components in mafic rocks from 8 to 3. Water is omitted and assumed to be mobile. SiO2 is similarly ignored, equivalent to projecting from quartz. In order from a projected phase diagram to be truly valid, the phase from which it is projected must be present in the mineral assemblages represented. A typical ACF compatibility diagram referring to a specific change of pressure and temperature, the kyanite zone of Green's phases, etc. ACF values of some common minerals: talc, Mg3 Si4O10 OS twice, A equal to 0, C equal to 0, F equal to 100%. Anthophyllite, cummingtonite, Mg Fe7 Si8O22 OS twice, A equal to 0, C equal to 0, F equal to 100%. Hypersthene, Mg Fe twice Si2O6, F equal to 100%. Dolomite, Ca Mg CO3 twice, A equal to 0, C equal to 50%, F equal to 50%. Diopside, Ca Mg Si2O6, A equal to 0, C equal to 50%, F equal to 50%. Calcite, CaCO3, A equal to 0, F equal to 0 and C equal to 100%. Tremolite / actinolite, Ca2 Mg Fe5 Si8O22 OS twice, A equal to 0, C equal to 29%, F equal to 71%. Vishwavidyalaya, 10 CaO, 2 MgO, 2 Al2O3, 9 SiO22 H2O, C equal to 72, A equal to 14 and F equal to 14. Epidote, 4 CaO, thrice Al Fe plus 3 twice O36 SiO20 H2O, A equal to 43, C equal to 57, F equal to 0. Pyrophyllite, Al2 Si4O10 OS twice, A equal to 100%. Kyanite, sillimanite, andalusite, Al2 SiO5, A equal to 100%. Stellite, 2 Al2O3 FeO, 2 SiO2 H2O, A equal to 67 and F equal to 33 and C equal to 0. Chloritoid, FeO, Al2O3, SiO2 H2O, A equal to 50, F equal to 50 and C equal to 0. Almandine, Fe2, Al3, Si3O12, A equal to 25, F equal to 75. Chloritoid, 2 MgFeO, 2 Al2O3, SiO2, F equal to 50 and A equal to 50%. Wollastonite, CaSiO3, C equal to 100%. Anorthite, CaAl2, Si2O8, A equal to 50, C equal to 50%. Lomentite, CaAl2, Si4O12, 4H2O, A equal to 50, C equal to 50. Lawsonite, CaAl2, Si2O7, OS twice, 4H2O, A equal to 50 and C equal to 50 and F equal to 0. Chlorite, variable composition, F equal to 90 to 65, A equal to 10 to 35. Mg5, MgAl, AlSi, Si3O10, OH8 up to MgFe4, Al2, Al2 Si2O10, OH8. Hornblende contains, in contrast to tremolite, variable amount of Al2O3 and MgFeO. Their CO content varies somewhat as well. Therefore, the composition of various hornblende must be shown by an elongated field on the ACF diagram extending from the point presenting tremoli towards the A corner. Similarly, biotite extends from F corner to about A equal to 18 and F equal to 82%. The ACF diagram is useful because the mineral assemblages of different bulk composition metamorphosed under a range of pressure and temperature can be presented in this diagram. Peltic composition will appear near A site, ultramafic composition near F, and calcareous composition will be near C site, and basic composition in the middle of the diagram, but lightly shift towards F corner of the ACF diagram. Dear student, today in this lecture we have discussed about the ACF diagram. I believe this lecture was useful for you. For further studies, please read the textbooks, references and links given in the text. Thank you very much.